now that we know which two reflected rays are going to interfere with each other, let's try to derive the equation to understand in which situation it will be a constructive interference, in which situations it will be a destructive interference. So our syllabus restrict ourselves to rays that are incident normal to the surface of the thin film. So if our thin film is being oriented horizontally, our ray will be coming down at a vertical direction. So the ray will have to be perpendicular to our thin film. So here we have our thin film with a thickness of small t over here, and we have light rays being incident onto the boundary between medium 1 and medium 2. So essentially, you have light being incident on the upper surface of the thin film. So here, you might expect that the reflected ray, you need to think whether there's a phase change happening to the light rays or not, to the light waves or not. Okay, so medium 1 has a larger index of refraction, medium 2 has a smaller index of refraction. So if you go from high index of refraction to low index of refraction, high to low, there is no phase change. So for this position here, you should expect that the reflected ray will reflect on the same side. There's no flipping, there's no shifting. So if the wave arrives on the left hand side over here, it should return or it should get reflected starting with the left hand side as well. So this is the reflected ray, which undergoes no phase change, and the refracted ray will never undergo phase change as well. Reflected, you need to consider whether there's phase change. Refracted, there's no phase change that will occur. Okay, so this one is very straightforward. For the ray that gets transmitted or for the ray that gets refracted into medium 2, there's no phase change over here. Okay, but for the reflected, we need to consider, but since it's high to low, that's why there is no phase change over here. Okay, so no phase change for the first surface. Now the transmitted wave or the refracted ray will arrive at the boundary between medium 2 and medium 3. Essentially, it has arrived at the lower surface of the thin film. So again, your light will get reflected and refracted here as well. So we need to consider whether the reflected light wave, whether there's any phase change or not. So medium 2 is larger in terms of index of refraction. It has a higher index of refraction compared to medium 3. So again, medium 2 to medium 3 is a high to low. So high to low, again, there is no phase change that will occur for this boundary over here. So you should expect that the reflected ray will reflect on the same side. If the waves arrive at the boundary on the right hand side, then our reflected wave will also start on the right hand side, going back upwards. Okay, of course you have your refracted ray which get transmitted into medium 3, but that's not our concern. Our concern are on the reflected wave. Okay, so we know that when this blue reflected wave gets transmitted out to medium 1, then it will then interfere with the brown reflected wave reflected from the upper surface. Okay, so what's reflected from the lower surface here will interfere with what's being reflected from the upper surface of the thin film. Okay, so this is a scenario that we are going to analyze, but to simplify our understanding, what I'm going to do is I'm going to split our diagram into two separate diagrams. Just now everything I'm trying to explain how everything comes into place. Where do you get the first reflection? Where do we get the second reflection? But now I'm separating it out to show you clearly that this is how the first reflection happened. So you have a light wave arriving at the first upper surface, then you get reflected with no phase change. This is how you get the first reflected wave. Okay, the second reflected wave, you can get it by having the light wave transmitted through the boundary between medium 1 and medium 2 first. Then it arrives at the boundary between medium 2 and medium 3. It gets reflected over here. For this case, there's no phase change. And then it gets transmitted out, or it refracts out from medium 2 into medium 1. Then only it will arrive at the same region as the first reflected wave. And these two reflected waves will interfere with each other. Okay? So we can predict that if it's a constructive interference, the difference in the path between the second path and the first path should be equal to m lambda. This is what we have been discussing all along. If it's a constructive interference, the difference in the path traveled to get the first reflected wave and the path traveled to get the second reflected wave, the difference in distance between these two paths will be equal to m lambda. Okay, whereas if it's a destructive interference, the difference in path will be m plus half lambda. So this is the characteristic we have been discussing all along. But what is our path difference over here? We know for sure that R2 here is a longer distance because you have to enter the thin film and exit the thin film. R1 is a shorter distance because it never really entered the thin film. But how much does it differ between R1 and R2? So if you observe R1 and R2, we see that the upper medium one path is actually the same, but the only difference that we can see here is that R2 undergoes an extra downward traveling to the boundary between medium 2 and medium 3, then get reflected out to the boundary between medium 1 and medium 2. So this portion here, this to and fro over here, is the extra journey traveled in order to obtain the second reflected wave. The first reflected wave, you don't need to go into the thin film. There's no to and fro in the thin film for the first reflected wave. But for the second reflected wave, you have to travel an extra to and fro to get the second reflected wave. So this is the extra distance traveled in order to get the second reflected wave. So the path difference will be one time going down the thickness of the film, one time going up the thickness of the film. So this time it will be twice the thickness of the film as the difference in path between R1 and R2. So we can change R2 minus R1 to be represented by 2t over here. So if our 2t is equal to m lambda, if the thickness over here, if it times 2, that value here is an integer multiple of lambda, what happened is it will your wave coming out in medium 1 over here will constructively interfere. Okay, however, let's not talk about destructive first. Let's focus on the constructive. But however, the problem is we usually don't know the wavelength in the thin film. Okay, we usually are familiar with what's the wavelength of the light when they are in vacuum or when they are in air. But when they enters water, when they enters glass, we know that the wavelength will change, right? But what wavelength will become is usually difficult for us to determine. So it's better that we express this equation in terms of lambda vacuum or the vacuum wavelength that we can easily obtain. Okay, red has a specific value, yellow has a specific value, blue has a specific value for the vacuum wavelength. Those you can just look it up on in Google, then you can find those wavelength. But lambda in water, lambda in glass, all of them are very case by case kind of value. So it's inconvenient to express this equation in terms of lambda film, which is a wavelength in the film. Let's re-express this lambda film in terms of lambda vacuum. That will be easier. Okay, we can use the same thing that we have discussed in the previous video, where the ratio between the wavelength is actually the inverse of the ratio between the index of refraction. So we know that the index of refraction for vacuum is 1, so we can replace index of refraction for vacuum with 1 and the film remains. So you can just substitute out lambda film over here with 1 over n film multiplied by lambda vac. Okay, so now if you shift around the equation, you get 2 index of refraction of film multiplied by the thickness of the film is equals m lambda, but this time the lambda is a vacuum wavelength, which is an easily determined value. We can just look it up in your Google. Okay, so this is the constructive interference. The idea is if you have a thin film with a particular thickness, and if you do 2nt and it's actually equals to an integer multiple of the wavelength that you shine onto the thin film, then what happens is the light will get reflected in a strong manner because it will constructively interfere with each other. Okay, m over here you can substitute 1, 2 or 3, but you cannot substitute 0. Technically, I don't think it's appropriate to say that you need plus minus. Okay, I don't think it's necessary. Okay, there's no negative case to talk about. Okay, so but the idea is you cannot substitute 0 over here. You're not supposed to substitute m is equal to 0, because if you substitute m is equal to 0, if you calculate everything, the thickness will be equal to 0. Thickness equals 0 means that there is no thin film in the first place. Okay, but we say that there's a thin film already, right? So it's not reasonable for us to put 0 here because we don't want a 0 answer for our thickness. Okay, so this is the equation for constructive interference, and I believe you use a similar thing to derive, a similar manner to derive our equation for destructive interference. You replace R2 minus R1 is 2t, then you change your lambda film to become 1 over n film times lambda vac. So you do the same thing and you get an equation for destructive interference. So it's a similar idea, just that if you calculate 2nt, that value, it's an integer 0.5 multiple of the vacuum wavelength. Okay, it's 1.5, 2.5, 3.5, 0.5, so on and so forth. Okay, for the M over here, you can substitute 0 in here. There's no problem to substitute 0. Why? Because if you substitute 0, it won't cause the thickness to be equal to 0. So that means the thickness will still be a non-zero value, and that perfectly makes sense. There's nothing to worry about. In fact, if you substitute 0 over here, that will be the thinnest possible thin film that you can get to get destructive interference. If you want the minimum possible thickness, you substitute m is equal to 0 for this equation. If you want the minimum possible thickness to have constructive interference, then you substitute 1 into the equation for m, then you can get the minimum thickness for constructive interference. Okay, so this thin film can cause constructive interference to certain wavelength. It can cause destructive interference for certain wavelength. Okay, if that wavelength, if you integer multiple it, let's say red light. Okay, let's say you put red light, you have your red wavelength over here. If 2nt is an integer multiple of that red light wavelength, then you will see red light being reflected strongly. But let's say if you substitute blue light, and you find out that this value over here is actually a 0.5. Okay, you calculate 2nt already, then you put in blue wavelength, then you get that, oh, it's actually a 2.5. So if there's a 0.5, it means by if you shine blue light on it, the blue light will actually cancel each other out for the reflected ray. So even though you shine blue light on it, you will see very minimal blue light will get reflected out from the thin film. Okay, so if you shine red light and blue light simultaneously on the thin film, what you see, you only see the reflection of the red light. You will not see the reflection of the blue light, because the red light will interfere constructively for their reflection, but the blue light will interfere destructively for their reflection. Okay, so that's the idea over here. So if you shine white light on your thin film, we know that white light is actually a continuous spectrum of rainbow colors, right, that we usually talk about. We talk about dispersion of light. If you disperse white light, you get a spectrum of colors, right? So if you shine white light onto your thin film, that white light consists of a wide spectrum of colors. You have red, orange, yellow, the whole rainbowish color. Certain colors, their wavelength will constructively interfere. Okay, so let's say red, it will constructively interfere. But certain wavelength, it might not constructively interfere. It might destructively interfere. So let's say green destructively interfere. I'm just randomly giving an example. So let's say red is constructive, but green is destructive. Purple is constructive. Blue is constructive. Yellow is destructive. So there are certain colors that will cancel each other out. There are certain colors that reflect strongly. So when you look at the thin film, you look at the thin film, the reflection of those light will come into your eyes. But only a portion of that spectrum will arrive at your eyes, because some of them get cancelled out already. So what happens is, you will not see yellow, because just like I said, yellow destructively interfere, right? You will not see green, because green destructively interfere. What you might see is just the red, the blue, the purple. Okay, so that's why when you look at a thin film, you seem to have like a rainbowish kind of hue coming out from the thin film. You might see that those thin film, those soap bubbles, those oil spill, seems to have a rainbowish hue. It's not because that they are emitting light in the rainbow spectrum. It's just that when you shine light on it, there's a portion of the light get cancelled out for their reflection. So you are only seeing the remaining portion of the light that gets reflected out strongly. So that portion of light that gets reflected out strongly is only a portion of the rainbow color. So you're not able to see the white light that gets reflected off it. You're only able to see the portion of it. That's why it sort of have like a rainbowish hue, because it's missing some color. It cannot be white anymore. Okay, so you see those kind of rainbowish hue, which we have described in the previous video. Okay, so this is how you derive the equation for constructive interference and destructive interference for the interference of reflected light in thin films. But now the scenario that I'm talking about is N1 larger than N2, N2 larger than N3. In the next video, we'll consider various other scenarios in which we change the index of refraction of the medium, and we introduce phase change to either one of the surface over here, and we see what will happen to the equation for constructive and destructive interference.